Alright folks, so one big thing to discuss today, that's it, the Fundamental Theorem of Calculus. So most people enjoy this section, we'll see how you do. So the Fundamental Theorem of Calculus says, suppose you have yourself a nice continuous function f on a closed interval, and you know an antiderivative of it, okay, you've got one of these. Then in order to compute the definite integral from a to b of f of x dx, you just take capital F of b, your antiderivative at b, subtract your antiderivative at a. So that's it. This is what the big theorem says. Grab yourself a function, grab yourself an antiderivative, and you are in business to figure this thing out. Now, notice something very important right here. There are no limits in there, right? We know that this thing on the left we defined in terms of a limit of a sum, lots of computations, a bit of work. And what this theorem says is that based on what we've done so far, well, we can just substitute and compute with an antiderivative. Now let's take a little bit more detailed look about why we should believe that this is true. Well, the first thing to note is we're given that f is an antiderivative, and we saw before that what this means is that f of x looks like this for some alpha. It's a definite integral from alpha to x, a function of f of u to u, for some number alpha we haven't picked yet. So let's examine the right-hand side. It says it's f of b minus f of a. Using the antiderivative, f of b becomes this first integral where we replace the upper limit with b, and f of a we can replace with an integral as well, but now our upper limit is a. So let's look at geometrically what this difference of integrals is really representing. So geometrically, what we're going to do is we're going to try to integrate from a all the way over to b. And what we have is we have these two integrals. We have the integral that starts at alpha and goes all the way to b. So this will be our first integral here. So it's going to calculate this area for us from alpha all the way over to b. And second, we've got the integral that goes from alpha to a. So it represents this area here. So when we take their difference, what we're going to be left with is we're going to be left with this region over here I've colored in green. So what that means is when we take their difference, all we're going to be left with is the integral from a to b of f of u du. And this is exactly what was on the left-hand side in our theorem here. So this means that this makes sense. When we take and subtract f of b minus f of a with the antiderivatives, the region we're left with is the integral from a to b, the definite integral there. And that's all there is to it. That's the fundamental theorem of calculus. Now let's talk about some properties related to this. So the first thing this says is that if you can find the antiderivative of your function f, you can find a definite integral without needing to use the limit of a sum or geometry or any of that stuff we did before. Okay, you don't need to do that. As long as you know your antiderivative rules, you can do it. It's nice and easy. The second thing is you want to be aware of some shortcut notation that's pretty common when using the fundamental theorem of calculus here. So the shortcut notation is that we have this intermediate step here where we have a vertical bar that shows our antiderivative very abstractly as a function, the upper and lower limits, and then we go ahead and substitute it in. So let's just see this thing in action. So what we have here is we have that the antiderivative of 2x becomes x squared, because we remember that's reversing the power rule for integrals. We move over our lower and upper bounds, and then we substitute them in. The 3 goes in the first one, so it becomes 3 squared. The 1 goes in the second one, so it's 1 squared. And we get an answer of 8. So this means we've just integrated this function, and we got 8. No limits necessary. Another thing we need to do is we don't need to worry about including that c, that darn constant of integration. This constant is very, very important for indefinite integrals, but for definite integrals it just cancels. So let's look what happens here. So we started with our integral here, and suppose we decided to include our constant. Our constant's right there. Not a big deal. Then when we substitute 3 in, we get 3 squared plus c. When we substitute 1 in for x, we get 1 squared plus c. And what do you notice? Here we have plus c, here this minus becomes a negative c. They cancel out, so we don't need the constants there anyways. So let's look at some examples. If we want to compute this definite integral, we need to figure out what number this represents. And so the first thing we need to do in our process, step 1, is we need to figure out an antiderivative. So the antiderivative of t squared will be t cubed over 3 by the power rule, minus 2 times t, again by our power rule. And then we need to evaluate this at negative 1 and 1. And so the next step says, well, we need to first replace all of our t's with 1, so we get 1 cubed over 3 minus 2 times 1. And then we need to subtract what happens when we put negative 1 in for 3. And now it's a matter of just cranking through all of the arithmetic. 1/3 minus 2 minus, let's see, negative 1/3 plus 2 is going to be 2/3 minus 4 is equal to, I'm going to mess this up, negative 10/3. And I've just checked with the computer. No need to be questioning. Yep, that's right. Okay? Now this would have been awful having to do with the limit definition. You can try it for yourself, but it would have been a bunch of work. This way is much nicer. For this next example, we're going to compute the integral from 0 to pi of sine of x dx. Now I don't want to say this would have been impossible to do with the limit definition. I'm just going to tell you that it would have been awful. But what it's going to end up calculating, it's going to end up calculating this area here between the sine curve and the axis from 0 to pi. So let's look at this. Well, so the first step is we need to find an antiderivative, and we know that the antiderivative of sine is going to be negative cosine, because if we take the derivative of negative cosine, we're going to get sine. And so now we need to substitute in our bounds. So we take negative cosine of pi minus the negative cosine of 0. And now either you get out your calculators or you check and see, did I remember these things correctly? Well, let's see. This is going to be negative cosine of pi, which is negative 1. So don't worry, there's a lot of parentheses, but it's okay. Minus negative, well, what's cosine of 0? It's 1. Good job. Oh, extra parenthesis. So what did I get? I get a 1 plus 1 equals 2. The area in here in blue is 2. Now, you probably wouldn't have actually guessed that just by looking at it. There's no reason to think that this is 2, but as it turns out, it's pretty neat. It's just an area of 2. Just for fun, compute the integral from 0 to pi over 2 of sine of x dx and see what you end up with. I bet you'll end up with something pretty neat. I suggest you try it. So let's try to compute a real integral now. Alright, so let's try to compute the integral of this mess. Well, the first thing I'm going to do is I'm going to try and break it up into pieces. So the integral from 1 to 5 of t squared sine of t dt plus the integral of 2t times cosine of t dt from 1 to 5 again. And now if I stare at this for a while, I'm going to realize I don't know how to compute these. These are not ones that I know how to compute, and I'm stuck. Which means we need to be careful. You still have to be able to compute an antiderivative. I don't know what my antiderivative function is here. I don't know a function whose derivative will give me this expression up here. Therefore, I'm stuck. If I had to compute this, I got the limit definition, maybe some geometry, but it can sometimes happen that you get stuck. Integration is a lot harder than taking derivatives. So here's another one, an integral where you might look at and think, maybe I'm stuck. I don't know what to do with absolute values. So occasionally we have to use geometry just a little bit. So let's look at the graph. So this integral is saying compute the area from over here at 0 all the way to 4. And to do this, what I'm going to do is I'm going to break it up into two pieces. Piece A and piece B. So this integral here, really, we can compute by computing the integral from 0 to 2 of the absolute value of x minus 2 dx, plus the integral from 2 to 4 of the absolute value of x minus 2 dx. So what I can do is I can compute this first integral by saying this is going to be equal to the integral from 0 to 2 of the negative, because that's what my line is here. The line here is really the negative of x minus 2. And I can add to this the integral from 2 to 4 of x minus 2 dx. Now at this point, just for kicks, let's practice using the fundamental theorem of calculus again. So in this case, this first integral, what I have is I have a negative times x squared over 2 minus 2x. I will evaluate at 0 and 2, plus x squared over 2 minus 2x evaluated at, whoops, that was a mistake. I want to evaluate this one from 2 to 4. And when I compute these things, what should hopefully happen is for the first one, I'll get 2. For the second one, I'll get 2. And I'll end up with a total area of 4. And you can also quickly compute geometrically what the area should be, and that we can see matches with our fundamental theorem of calculus here. So the fundamental theorem of calculus seems to work pretty well in most circumstances. So that's it. This is our big idea for the day. So I suggest you go and practice doing these problems. And if you're doing this over break, have a nice break. As always, try the quiz online, post a question, and I'll see you in class. Have a good night.